You're probably going to have to click on got it on your screen now. I thought about how to make the most out of this one-off remote lecture, and what I decided is that we're just going to try to do an interactive MATLAB exercise, hopefully together. And so if you haven't already done so, oh, and I will share my screen so that you can see everything I'm doing. Okay, so I've put, I've put both the MATLAB script as well as the data that we will be working through under content. So under code and data sample. So the code for today is here and the data is here. And it's important that where you download the code and where you download the data file, the mat file, which is called crypto.mat, and the script, which is called demo svd.m, are both in the same folder. I'll explain why in a second. In general, if you're unsure how to set up your project structure, if you dump everything into the same folder, you should be good to go. But if you have large projects, then you'll have to have a certain path layout. And if you're working with other people, you're going to have to enforce the same kind of project structure across your team members. But here, we're just going to do a very straightforward application of a really useful piece of linear algebra called the singular value decomposition. And I chose this data set because I think it's a little bit timely. We're going to be looking at cryptocurrency prices across time. It's also a real world data set. It's also the type of data that many amateur and professional traders are interested in understanding, to be able to forecast it, to be able to discover the structure in this data. And so I think whenever possible, I will try to have us actually look at some real data and hopefully in the process, give you some insight into the things that you need to do to get real data to work. Because oftentimes the difference between a synthetic data set and the real data set is that there's some pre-processing that needs to be applied to real world data to get the algorithms to work. And so I will show you a little bit of that today. Before that, I do just want to put up, before we actually delve into the script, I do want to show you just basically one equation that describes what the singular value decomposition is, mathematically, formally. And so, again, this is one of these examples where I think that this is the way it's taught. And I remember definitely when I first saw this equation, I can't say that I was able to glean a lot of geometric or mathematical insight into it. I will try to unpack it a little bit here, but then I think you will really understand what the SVD is doing once we apply it to our crypto data. Okay, let me just make sure that there's no one else in the waiting room here. How do I get back there? I have to stop sharing for just 1 second. Just want to make sure that there's no one else trapped in the waiting room. Okay, we good. Okay, so the SVD is first of all, it is a decomposition. So decomposition means, so A is the matrix that you have. A is your data matrix. And what the SVD does is it factors it into a product of three matrices. So right away, you think, why would we want to do this? Why we have one matrix with, let's say, m times m rows and n columns, and we're gonna factor into three matrices. Why would this be helpful? So the key thing here is that matrices. So S is easy. S is a diagonal matrix. And so maybe we'll start there. S is at the diagonal elements of S are called the singular values. And a word that gets often used here are modes. So your data matrix has certain modes. And you can think of each each diagonal element of S as capturing the strength or intensity of the n modes in your data matrix A. So S is diagonal. U and V are not diagonal, but they are orthonormal. So orthonormality consists of two properties. The first one is that the length of all the column vectors is equal to 1. So here we go. So orthonormality means that every column of the U matrix and every column of the V matrix is equal to 1. And every column of U is orthogonal to every other column of U. So in other words, I don't know if I can. Basically, remember I told you earlier that you should think of a matrix as a set of vectors. So each column is an element of that set. So these vectors in matrix U all have the same length, a length of 1, and they're all perpendicular to each other. And the same thing is true about V. So basically what this decomposition is doing is it's kind of reorienting your data into a set of perpendicular coordinates. So that's all I'm going to say here, because I think that it's more, you'll get more out of it once we work through the example. Okay, so now, I can't, I only see my MATLAB terminal, but hopefully you guys were able to download the data and the code, and you can work along with me as I do this. You'll learn more, you'll get more out of it if you actually get to see the variables as they're generated on your end as well. So what I'm going to do is I'm going to execute the script one cell at a time. So in MATLAB, the 2% signs delineate cells. So a cell is like a bunch of code that has like a logical grouping. And I'm going to execute one cell at a time. For me to do that, I'm on a Mac, so I press Command Enter. And when I may be different on Windows. On Windows, it may be Control Enter, maybe Shift Enter, or something like that. Windows Enter, I don't know. So give me just 1 second. So I've executed the first cell here. And there's a couple things. In my workspace now I have, which hopefully for you is also on your right, I have the variables that have now appeared. I can see those variables in the command window if I type who's. And so I see that now I have 3 variables. Crypto file name is the string. So that's just equal to crypto.mat. The path, so this means right here. This means that this is a relative path to the present. So if I did this, that means 1 level back. If I did this, it's 2 levels back. So the 1 dot just means right here. In the present, it means present directory. And so the important variable here is called data. And as you can see, it's a struct. So I'm going to scroll up a bit here. And I'm gonna enter data, just type in data, enter, and then you should see that MATLAB tells you what fields are in my struct. So a struct is it's kind of a higher level data structure in MATLAB that lets you store different types of data in kind of one meta array or structure. And so in this case, data, and I created that by loading in this mat file, crypto.mat. And so I see that the fields of my struct are the prices, which I'm going to plot in just a second, the timestamps, and the names of the cryptocurrencies that I provided for you here. So the 391 dimension here, as I'm sure you can guess, that's the time dimension. So here we're looking at prices of these currencies over 391 timestamps, and I can tell you that they are, I believe they are 12 hours apart, something like that. And the 19 here refers to 19 cryptocurrencies. So ADA, BAT, BNB is the Binance coin. I'm sure you know that BTC is Bitcoin. BitTorrent token, I believe. Ethereum Classic, I think, and this is Ethereum. I actually don't know any of the other ones, but there's a bunch, and I'm only giving you a snippet here of them. I'm only giving you 19. So one of the first things you want to do, so first, before we actually visualize the data, we're going to, I don't want to have to deal with this struct forever in my script. I just want to rip out the variables that I need. So in this case, the variables that I need are all three of them. So when I execute this and I type in whose, I see that I now have standalone variables for prices, timestamp, and names. Now those variables are no longer just bound to my data struct. Okay, so if you have those in memory, you should be able to execute the cell that starts on line 15. And we're gonna pop up our first figure window. Okay, I'm trying to blow this up. All right, so right away, it looks strange, right? So let me ask you guys. So what is evident about the data from looking at this plot? See, I know if we were physically in class, somebody would answer by now.
One of the currencies is worth substantially more than the rest of them.
Exactly. So it's I think it may be more than one actually. There's a couple of outliers here when you actually even, so for example, if I select this one and I delete it, oh, come on. No, I don't want to inspect it. I want to delete it. Okay. Let me see. Let's see. Maybe this one. No. Come on. Maybe this one. All right. So now I deleted it. Oh, actually, no, you're right. It's totally just one. I thought it was more than one, but it's not. It's probably Bitcoin. But here's the thing. There are many reasons why you should consider not operating on a data set that has that property where one channel, in this case, one cryptocurrency, is like orders of magnitude larger. And the main reason is that in many cases, and I would argue in this case, the actual value of the price is not as important as the fluctuations and the relative fluctuations around each currency's mean. And so I would argue, for example, that this whatever color this is, purple or something, probably Bitcoin. It's not, Bitcoin is not actually, like, the significance of Bitcoin is not actually, you know, 1,000 or 10,000 times greater than the other currencies. And so it would not be a good idea to start computing statistics on this multivariate data as is. And so actually, before we do that, I think what I do is I also show you the, so the time, notice the timestamps. If you ever work with data that has been clocked by a computer, you'll see numbers like this. They usually start with 738,000. So I believe the units of these timestamps, this is the most rigorous way of representing time. I believe this is number of hours since, like, this may be wrong, or maybe number of days. Let's see, if I 738 divided by 365. Yeah, it's a number of days since since, let's see, 0 AD, would that be correct? It's number of days since 0 AD. And so the fractional part is obviously very important here, right? Because this is days. And this fractional part is going to give you information as to, like, as to hours, minutes, seconds, which we here we need. By the way, when I see this has only been 738,000 days since 0 AD. You kind of get, I feel like the perception is that there's been more days than that, but it's actually not. Yeah, at least to me, it's a surprisingly small number when I see it. Okay, but I don't want to work with these timestamps. I don't want to work with these crazy fractional number of days. So I'm going to convert it. And so this is kind of a double function. So the first thing I do, and I'll actually unpack it here. First thing I'm going to do, there's a datevec command which will allow me to convert a given timestamp into an array that tells me that gives me the year, month, day, time, and this is a UTC time. It's not Eastern time, and so this is 9/11 of 2020, and it's 8:41 UTC time. And after that, what I can do is I can convert that vector to a string, and that string, you know, can be whatever you want. I can just do month, day, year. I believe I can also do hour, minute, second if I want it. I don't really, you know, here in the example in the code I gave you, I just convert it to month, day, year, because the sampling rate is not that fine. And what I'm going to do now is I'm going to plot this same data, but I'm going to plot it. Oh, I'm going to plot it in axis 2, but with timestamps indicated. So you can see more easily the length, the duration of the period that this data covers. So it covers from the fall of 2020 up to, and actually this is January of this year. So this is, I got this data fairly recently. It's pretty up to date. Okay, so now we've loaded in the data, and we have been able to plot it using calendar time, and we kind of see the general trend across time. So now comes the important step of normalizing or standardizing the data. So there's 2 steps that I'm proposing should be done to this data set. step number one is to remove the mean from every time series. And so I'm going to execute this. Okay. Do we have a question or is it just background noise? I can't see any of you when I'm in share screen. Okay. So size of prices is an array of my prices. It has 391. It has 391 rows, time points, and 19 columns, currencies. I'm interested in getting the temporal average of every currency. So just one number per currency now. Okay. And the comma one here, which is optional because it assumes that you're taking the mean in the first dimension. But I put it in here just to be explicit that we are taking the mean along the dimension of time. And now means should be a 1/19 array. And if I output it, I've outputted the means here. What you will see is that the means of the currencies vary wildly. And so currency number 4, which I believe is probably Bitcoin, right? 40,000 sounds about right for Bitcoin. So if I look at the names of 4, so actually one thing, MATLAB has this nice table feature. Oh, come on, really? How do I do this? No, it won't let me. Let me do this. No. All right. I was gonna try to render it as a table, but let's see. I've actually started using this. It's not gonna work. I don't understand why it won't let me make a table with. There we go. That works.
Maybe transpose both. I think means
Yeah,
also a row vector.
Thank you. Yeah, there you go. Transpose. Thank you. Transpose both, exactly. So now you can, and I use this table. This is like MATLAB's, if you use Python, like Python has, or Pandas has data frames, and there are different kind of containers. I think container is a technical term for this. So table is a nice little container that lets you, the nice thing about it is it lets you store heterogeneous data into the same structure. So like the variable name 1 is a string, variable name 2 is a numeric, and it lets you combine, and you can, in the elements of the table can actually be arrays. So you can put like, it's very flexible. And so here you see that if I plot, if I show the means for each currency, you can see that Bitcoin has the largest mean, right? And because its coin is worth, 1 Bitcoin is worth the most. But getting back to the argument about the absolute price not being important, a big factor here in assessing in the prices is, well, how many Bitcoins are there? The reason that 1 Bitcoin is worth 40,000 is because there isn't as many Bitcoins as, let's say, Ethereum or something else. And that's why I'm going to normalize the data. Okay. And if you don't know anything about cryptocurrency, don't worry about it. You don't need to, this is just an illustrative example. The next thing I'm going to do, in addition to getting the mean, is get the standard deviation. So this is essentially the power. So it's standard deviation is completely independent of the mean. You can have a mean of 0 but a high standard deviation. You can have a very high mean with low standard deviation. Standard deviation measures the fluctuation around the mean. And so this tells MATLAB that I want to compute the standard deviation in along the first dimension being time. And I'm going to do the same thing here. I'm going to do a table. So now I see And there often is a correlation between a mean and standard deviation. So generally, the larger the mean, the larger the standard deviation, because if your values are larger, the fluctuations are often going to be higher as well. And so here we see that, so the ratio of mean to standard deviation could be taken to be a proxy of stability, for example. So, for example, I'm going to add this to my code. I'm going to call it SNR, or I'm going to maybe, yeah, SNR it's usually. So if I divide the means by the standard deviation, and then I add it to my table, if I add it to my table, it's gonna see now all of a sudden we have numbers when we have numbers in variable 4 that all of a sudden are pretty uniform looking, with the exception of one, the USDC. That I guess someone has had the brilliant idea of calling their cryptocurrency the USD cryptocurrency. And as you can see, it has a huge, it has a, yeah, it's very stable, I guess. So it will be what? It will be number 15. So if we plot that one, 15, it should look very flat. And it is.
I don't know what that coin is, but it's also worth $1. It's hilarious.
Yeah. Hold on a second. It is worth $1. Oh wait, I wonder if this is the actual US dollar. No. Okay, I have to look this up now. Hopefully there's nothing. Stable coin. Thank you, Amilcar. I should have known you were gonna know. So USDC is called stable coin?
It is a stable coin, so like there are many stable coins. It's not the only one.
And so, but it is a cryptocurrency.
Yeah, it's just like people can buy dollars instead of like dollars, and they have it in the exchange, something like that.
Well, that is really interesting to know, because I didn't know that before doing this analysis. And we're going to see when we do the SVD on this data, it totally treats this one as an outlier. Now I'll explain it because it's a lot less volatile. Okay, well, there you go. So this is, yeah, the fact that it's worth $1 is hilarious. That's awesome. And then, but if we look at now, let's look at the other end. So that was the most stable of our coins here. Let's look at.
Sure. I'm sorry, can I just ask something?
Sure.
When I ran the code for the standard deviation of each time series, for some reason I get 1. Am I the only one? Do you guys have also ones, or maybe I wrote something wrong?
Do you want to share your screen? So, or is that?
Yeah, sure.
Okay. That way I can try to help.
So can you guys see my screen?
What
Here?
size of prices for you?
So I'm here, right? And if I
Yeah.
run this,
Yeah.
and then I did the table here in command window like you
Yeah.
did, I think I wrote the same line of code. And then I just get ones here, which I thought was so weird because your numbers are actual standard deviations.
Okay, so let's, can I see your, can you
Should I go?
do a figure plot of prices for me, like in the command window?
Yeah, sure.
Just all of them.
All of them, right?
Yeah.
Like this?
Yeah.
Yeah. So wait, because this, can you guys see it?
That looks, yeah, that's already being normalized. So I think what's happened, you know what I think has happened? I have a feeling that you've already, you did the normalization and then you ran. So if you, can you do me a favor? Can you put a break, can you type, click where it says line number 47? And it
Here?
should, yeah, I clicked just to the right, or yeah, breakpoint, add a breakpoint. Yeah, run to here.
Oh, run to here, sure.
Yeah, try to do that. And now go, you see up top, it's a press step.
Oh, yeah, sure.
Step, do one, yeah, and then do it again. And now type in, and now in the command window, can you type in STDs?
Mm-hmm.
That's correct. So I think what happened is, I think you executed line number 58. Let's see. I think what happens is, have you been, it's like you executed a cell and then you went back and executed it again. So if the
Oh.
standard deviations were already 1, because what the normalization, yeah, now do it. Oh, you have to,
Well, I'm just gonna
no,
remove
do,
this.
no, yeah. You just have to press step one more time. There
Okay,
you go.
perfect.
Okay,
Thank you so
good.
much.
Anytime. Okay, we're gonna go back to my screen. Okay, right. So I was thinking the USD coin is the most stable. Let's look at the least stable. Let's try to find, and so we can do min val, min index is equal to min, let's say SNR. And I see that the least stable is BitTorrent. I love BitTorrent. It's BitTorrent is the least stable cryptocurrency in our list, right? And you can see that if we plot BitTorrent, hopefully it will, yeah. Yeah, so that's, it had a huge spike. It had a huge spike. Let's see. I'm not gonna try to figure out what time of the year that was, but it had a huge spike at some point, and then it went back down. Okay, so now we have, let's see. We have the means and we have the standard deviations, right? So now I'm going to remove the mean from the data. So a RepMat here means repeat matrix. So means is a 1 by, so is it means is a 1 by 19 array. And I need to subtract the value of every currency's mean from every time point, right? So I want to recreate each of those time series, but now to have everyone's mean be 0. And so I'm going to execute this line, which basically will center every currency's value, and hopefully, all right. So I'm going to actually run it from the beginning. And it's going to look funny. Come on. The zoom bar is getting in the way. Okay. Right, so it still doesn't look right, right? Even though you can tell that now, what is this? So this is the original data. This is the original data with timestamp, with the calendar stamps. And now this is what mean centering has done. Every time series is now exactly half below and half above 0. But it still doesn't look right, right? This still does not look like a well-behaved data set because a lot of the curves are totally compressed while Bitcoin is out here, dominating. And so we also need to execute this line, which is going to divide each time series by its standard deviation. And so I'm gonna the zoom bar is gonna be a pain for this. and then a step. Okay, and I'm gonna go back to the window. And now I have, now I have a nice looking, this is a well-behaved data set, right? So this is just mean centered. This is mean centered and then compressed so that the power of the magnitude of the fluctuations in each currency are now equal to the same value, namely 1. So if I were to, and I'm going to do this after I exit the figure, if I were to compute the mean of every one of these time series, it would be equal to 0. And if I were to compute the standard deviation of each of these time series, it would be equal to 1. So this is nice because now I can see that there are definitely dynamics in this data set that are shared between all the currencies. So you can definitely see that something happened here last spring where the value of crypto kind of went up. And then sometime in the summer went down. But overall, there's a slow upwards ascent in this curve, right? Generally, the currency, the value difference from beginning to end is a positive number, which makes sense. Okay, so last thing I want to show you is before I do the SVD, is to just verify that the mean of prices is going to be equal to 0, right? It's a very small number, numerical precision, and the standard deviation is all going to be equal to 1. Okay, so this is the critical line here that actually does the SVD. So I am interested in capturing the modes of cryptocurrency fluctuations. I'm interested in capturing in discovering the structure of that. And so I execute my SVD. And the first thing I'm going to do is I'm going to look at the size of my 3 outputs. So U is a square matrix, has 391 rows and 391 columns. S is going to have 391 rows, 19 columns, and it's going to be diagonal, as I'll show you in a second. And V is going to be 19 by 19. So the way to think about this is that, and the reason I chose cryptocurrencies and not, for example, images, because if you have an image, both dimensions measure the same. Both dimensions are just pixels, width and height. But cryptocurrency, the two dimensions of my data array are qualitatively different. The row dimension was time, and the column dimension was currency. And so what the SVD has given me here is giving me a set of basis functions for each of those dimensions. And so just as a preview of what you're going to see in the next few figures, what I'm going to show you is the first column vector of U is going to give us a time course that is best expressed in the original data. And the first column vector of V is going to give us a stem plot. So it's going to give us 19 weights, one for each currency. Again, that best captures the variability in the original data. But before I do that, I want to look at these singular values. So you can think of S as being a set of eigenvalues. So if you have a square matrix, you can do an eigenvalue decomposition. But in most, in general, a matrix will not be square. And so you can't do eigenvalues on a rectangular matrix, but you can always do an SVD. An SVD is one of these operations where every single matrix has an SVD. Not every single matrix has an inverse, but every matrix has an SVD. And so it's like probably the most widely performed it basically can be used to as part of the computation of many other algorithms. So what I'm going to do here is I'm going to plot the singular values. I'm going to show you what they look like. And so I have 19 of them because my matrix, the rank of my matrix, so the number of linearly independent rows in my matrix is 19. So I have 19 singular values. So they're ordered from highest to lowest. And this is this first singular value. You can think of it as your first eigenvalue or your principal eigenvalue. It's the strength of the most dominant mode of your data. The other thing to note is that you often see this kind of exponential looking shape. And the modes that have a singular value near zero are less important. So in many cases, we can let's say chop out the last, I don't know, 4 or 5 modes of this data, and we would essentially be able to recreate our data matrix with only 15 dimensions, but still capture all the variability. Because the sum of these 19 values here is the total power in the data. And we see here, the other thing is that the first singular value, the first mode, has a very large value. And I'm going to try to get you to guess when I show you the corresponding column vectors of u and v for the singular value. I'm going to try to get you to guess what that first mode is actually referring to. Okay, so let's look at now the first column. Remember that the columns of u are matched to the singular values. So that when I'm gonna plot this first column of u, and it's going to correspond to this singular value. So in other words, the column vector that the row, it's a time series essentially that I'm plotting here. This is the most dominant temporal mode in my data. And so let me ask you guys, see if anyone can guess as to, actually, let me plot the corresponding v vector also. And now I'm going to give you a stem plot of the first column vector of v. So remember, v is 19 by 19, u is 391 by 391. I told you that u was the temporal basis and v was the cryptocurrency basis. So now I'm going to plot all of those. So this is my first temporal basis vector, and this is my first currency basis vector. So I'm going to ask you guys if you can guess, and this time series and this stem plot are associated with this singular value, the first one. This is the first mode of our data. So can anyone guess as to what this time series and these stem plots are capturing in the data? Just intuitively. I don't mean mathematically. What do you think it means that this is the most dominant? You can think of it as a pattern. This is the most dominant pattern in my original cryptocurrency data. So what does that pattern mean?
It shows the average fluctuation of all of them.
That's awesome. That's exactly right. That's exactly right. That's exactly what it is. This is the global trend, right? So the way that in economics or even in the brain, when all the brain is doing one thing, going in the same direction, or an economy, to give the cryptocurrency market, this is the global signal here. And the reason, and what's really cool, and I didn't think it was going to come out this clean. This stem plot is basically flat, right? All of these are basically hovering around the same value, except for this USD coin, which is kind of funny. But what this is saying is that the first mode of our cryptocurrency data is just the global trend, right? So on average, this is the pattern that was observed in the overall cryptocurrency market, right? So there's a real physical intuition here as to, and you see that it's much. This mode captures a lot of the variability in the data. So if I were to take the outer product between this vector and this vector, I would do a pretty good job of capturing that matrix of observations with just one dimension. Okay, and so now what I'm going to do is I'm also going to plot in the fourth panel here. I'm going to plot the mean, just the raw mean, and I'm going to try to show you that the raw mean of the data really closely matches, not scale, of course, because the SVD is orthonormal. But you see that this is just the mean of my prices before doing the SVD. And you see that it looks very similar to our first, the first mode. And so sure enough, and this happens quite a bit actually, when you run SVD on your data set, oftentimes the first mode will just represent the mean of the data set. So now if I go back to here, I want to see if I can annotate with test. So if I were to write A is equal to U, right? This is just a column vector times, this is MATLAB notation, right? If I were to, this is just taking the first dimension of my 19-dimensional data set. This matrix A would already have a lot of the structure that is present in my original matrix A. So this will be called, see if I can get back to it. This will be called a rank 1 approximation of my data. I think I may actually do it later in the script, or I do everything except for it. So, so rank, if you guys remember from your linear algebra class, rank is the number of linearly independent rows or columns in your data matrix. So what I'm doing here is so U of 1 is, let's see, oh, I gotta get out of annotation. It won't let me do everything. So U of 1 is here and V of 1 is here. And if I multiply these two together, I'm going to get something that looks very much like my original data matrix. Why? Because it captures so much of the power in my overall data. So now, you know, so the first mode was very easy to interpret, but one could argue that it's not that interesting, because, you know, it's just a global trend. Yeah, we know that cryptocurrencies, like most assets, appreciate over time, but I want to know more. I want to learn something more interesting in the data. So what I'm going to do, and another way of saying what I just asked is, I want to capture the structure of cryptocurrencies beyond that is predictable from just the global market, right? So I'm interested in things that, I'm interested in dynamics that go beyond just what the average market trend is. And that's what these second modes are going to give you. So now we're going to create a new figure, and I'm going to just step to the first 8 lines or the first 9 lines. And so I'm plotting here is the second dimension of my data in both time and space. So this is where it starts to get interesting. Okay, so this is the second dimension. So I'm going to use the word pattern. Another word that is often used here is motif. So these temporal basis functions, basis vectors, the columns of U, can be thought of as temporal patterns or temporal motifs. However, be careful because when you do SVD, the sign, there's a sign ambiguity. So the fact that this is going, this is starting negative and then going positive, you could, if you flip the sign of this and flip the sign of all these, you get, the product will be the same. And so you can interpret the polarity of these temporal basis functions or crypto basis functions, but you can definitely interpret their dynamics kind of independent of the polarity. And so what we see here is that this trend here, right? So there's like a lot, whatever this motif corresponds to, currencies were going down in value and then started going back up. So there was definitely something happened at this point in time. And what's cool about this application of the SVD is you can tell, for example, actually, let me ask you guys. So looking at these two panels, which cryptocurrencies rebounded most strongly after this time 200 here? So you know, this is a motif, this is a pattern in the data. So currencies are going down and then they started going up. And I want to know, Amilcar says Ethernet. Let's see if, yes, Ethernet is exactly right. And why did you say Ethernet?
It has the highest value.
It has the highest value, exactly. Not just the highest, it has the highest value, also has the highest absolute value, which is nice, right? So the fact that it's positive means that Ethernet, again, in this temporal basis, did I say Ethernet? Ethereum, sorry. Ethernet, Ethereum, yeah. I'm old, man. Yeah, not Ethernet. Ethernet is great for providing high-speed internet with little loss, but Ethereum is a cryptocurrency that experienced the highest, that best expressed this pattern. And because it's positive, it went down, right? Because if you multiply this by this, you get the data. So because this is a positive number, Ethereum went down up to around 200 and then it started going up. On the other hand, these other cryptos that have, so let's look at EOS, whatever that currency is. It's probably trash, but it has a large negative, watch it be really popular in the future. But anyhow, it has a very large negative weight, which means that its pattern, all right, let me actually ask you guys. So this EOS, it has a large negative weight for this basis. So what does that mean about its dynamics during this period? It's flipped. Yes, yes, sir. It's flipped. So it was going up, right? So it had the opposite dynamics of Ethereum. It was going up until time point 200, and then it started going down. So in other words, you can argue that, so keep in mind, this is the second mode of the data, but the first mode is just the global signal. Right? The global signal is just, they're all basically going up. And so what we see here is that we can kind of make an inference that Ethereum and EOS were kind of working in opposition. So if, we have chat. So BTT, yeah, BTT said the same. Yeah, BTT was not, basically the fact that BTT is 0 means that it didn't exhibit this pattern. And so you can argue that BTT kind of just stuck to the global trend. But we haven't seen what BTT did in the third dimension yet, which we'll see in a second. But what the inference I was gonna make, and I wouldn't like stake my life on it or anything, but what I was gonna just, in a hand-waving way, make a claim that Ethereum and EOS are kind of anti-correlate or working in opposition. So if people are buying Ethereum they're generally selling EOS and vice versa. Okay,
I have a question.
yes,
So this is about, because you normalize the data before doing this. So this has nothing to do with the actual price, right? It's more to do with the the actual fluctuation.
that's right. Which I
Alright.
think is more meaningful though, because the number of coins in each currency is not the same, right? Like,
No, I'm just saying because I see USD, which is normally equal to 1, and I see the value is very high. You see USDC.
right, yeah, but that just means that what that means is that if you just look at USDC, it will have a strong, oh, you know why? Because USDC had no weight in the first basis. If we still have, do we still have the first figure? USDC had very little weight. USDC didn't follow this pattern, right? But it did kind of strongly follow it. So let's actually plot. It's a good question. Let's plot USD. I think it's 15. Sort of. It has a weird looking, is it 15 now? Yeah, it has a weird looking time series. It kind of expresses this downward trend, but in general, yeah, I guess your point though is well taken about, we are absolutely talking about everything that we're analyzing here is relative to every currency's price. So we're not looking at absolute prices like Bitcoin versus Ethereum. We're looking at normalized Bitcoin, normalized Ethereum. Everything has been compressed to the same scale. So the word you use, I think, is appropriate. We're looking at just the fluctuations relative to its own power, which I do think is very interesting. Okay. So now we're going to look at the third best. We're going to look at the third mode in the data. Okay. And here you see this, here is where the USDC coin really pops. So see, the USDC coin has a huge weight for the third basis. So this is what happens when you have one dimension that kind of is an outlier that behaves on its own. You will see this. You'll see that basis vector is basically 0 for everything except for that one outlier. And this temporal basis function is very similar to what we saw. This is essentially going to be a noisy version of the time series of the stablecoin, of the USDC stablecoin. So this actually worked out way better than I thought. Like, it's actually not easy to have a real world data set that can be interpreted easily, but this is really easy to interpret. So the third singular value, and if you go back to the original, where's my, here it is, right? This is the global mean. This is that Ethereum up, EOS down, and this is USDC. So the third mode of our SVD is capturing the USDC. This is capturing the global signal, and this is capturing that pattern where something happened around, I think, where was it now? Figure 3, right? This is the second basis, and this is the third. So all three modes kind of have some interpretation in the original data. So the first mode is the global trend. The third mode is this outlier coin, and the second mode is kind of like a certain coins. I would say that this dimension is the most interesting, actually, and the most information rich, because it tells you all the coins here that have a positive loading, this is another term often used as loading factor. So every currency that has a positive loading went down and then went up. Every currency that has a negative loading went up and then went down. Okay, so now I have, I'm going to recreate the data. So I'm going to recreate my data without the first SVD dimension. So why, and this is not uncommon in data analysis. I want to look at the data irrespective of the global market. So I want to capture only the fluctuations that are kind of genuine, localized events that would not be predictable by just knowing that currencies generally go up slowly over time. So so here's the line, this is the important line of code. So I'm going to take a second to unpack it. So this is a subset of matrix U, taking all the rows and all the columns except for the first column. 2 to n means columns 2 to 391. Similarly, I'm taking the entire diagonal matrix S except for the first row and the first column. So S here is gonna, so the size of S is 391 by 19. I'm gonna take rows 2 through 391 and columns 2 through 19. And similarly, V is a matrix that has 19 by 19. I'm gonna take all rows and I'm gonna take only columns 2 through 19. So you can basically take any subset of the columns here, and I'm going to create a modified version of my data. And if I've done it correctly, that data that I've created will now have everything in it except for the first mode. And the first mode we decided was the global pattern. So I'm gonna plot this. I'm gonna show you 2 views of the data, one as a time series and one as an image. Let's pull this up, make this as big as I can. Okay, I didn't put titles here, so maybe here. So here I'm gonna put okay. So notice that in the time series, you can see that this global trend that is in the original data has been destroyed. We've regressed it out of the data. And whatever fluctuations remain in here are fluctuations that would not be explained by just the market going up over time. Images are often very useful for rendering 2-dimensional data. And so here, this is the row dimension of this image is current cryptocurrency, and the column dimension is time. And so you see here it's blue, and then it kind of goes more yellow. So at the beginning of time, the currencies were lower than at the end of time. And now, but now when we remove the first singular value mode, we see that it's kind of like there's definitely punctate regions where there's things happening, like here. But this image is flat, like the corresponding time series. Okay, so we have 7 minutes, and I actually timed this fairly well. I have a question for you. You can either try to answer it if you've been following along and running this, you can answer it in your terminal, or you can just tell me on chat or verbally how what I should do to answer this question. My question is this: which currency exhibited the largest increase above that of the market. So irrespective of what the global market did, which currency went up the most during this time period? And I'm gonna shut up for a few minutes. I'm gonna let you think about it. I'm also gonna put up the data because it may help. So the question is, see if I can show both. So which cryptocurrency here went up the most above that of their global market trend? I need the Jeopardy music. I should have had it. Maybe I'll give a prize if anyone can figure this out. Cafe One, coffee. Susan, you give me a gift certificate.
Will it be like the second one? I'm just guessing.
I don't want you to guess. I want you to tell me. So remember, yeah. Let's see if, I mean, I guess one, yeah, I'm gonna give you guys another minute to see if you can, formulate.
You want is the question for the top graph or from the color map?
The top and bottom rows are the same.
Yeah, but we
correspond to
don't
the same
know
data.
exactly, but we don't
No,
know
no,
exactly.
Sure, sure, but if you tell me what operation I should do in my command window, I'll take that as an answer. But what I'm getting at is, what should I do with that data to answer this question? So which currency went up the most beyond that of the market, beyond that of the global market? You actually see economists talk about this a lot. Like you'll see things like Apple stock went up today, and then they'll say, and over the 6-month period, Apple had a 3% increase above that of the market, right? So in other words, stocks go up over time in general, but maybe Apple has gone up more than the average stock.
So
You mean within this defined time frame? It's like last
Yeah,
point
in this
first
time
point.
frame. Yeah.
So this last point minus first point, whatever is the greatest value for the
Yeah.
modified beta.
Yeah, that's right. Let's do that. Let's see what we get. So last point minus first point. So exactly. So we're going to do max delta, max end. Here's equal to max. And we're going to do modified prices, right? Because modified, we want to remove out the last point minus modified prices. I believe this is it. This should do it. Okay. And so now if I type in names, you guys want to guess which one is going to be? You guys know about crypto? No? Okay. Amilcar, you don't want to guess?
I mean, from the color map, I was saying the second.
Second, okay. Oh. What? Oh. Oops. I did, my bad. It's the other way. Ethereum. Max in is number 9. So we can do a sort to see if the second one was what? I don't know. So if you can do a sort here instead of a max. So Adam, you get a prize because this is the way to do it. Let's do the send. And then we can look at names. sort and so Ethereum, then Binance. By the way, this data is taken from the Binance exchange. So I don't know, it's weird to have the exchange trading its own coin on their own exchange. That seems weird, but anyhow, then Bitcoin, then the one that you were suggesting, Amilcar, then Cardano, and this. I mean, to me, this is really nice, right? If we, and it doesn't always work out this way for teaching, but these really are the 5 most salient cryptos in this list. Oh, maybe Ethernet Classic, I don't know. But these 5 are definitely more well-known than the other 14. So the fact that it came out this way is, for me, really satisfying that we were able to, remove the mean using the SVD, and whatever's left had this pattern. Okay, do we have is there any questions about anything that we covered today?
I guess this might take a little more playing with it, but I'm just looking, seeing that EOS is the last one, which you noted was the least corresponding to the second mode also. I'm curious how much of these results are governed by just one mode versus everything except for one. That question makes sense?
Yeah, so you can, so I did this because, right, so so for example,
If modified prices are just the second mode instead of 2 to n, would it be drastically different?
we can do that. What I'll do is, I'll just do the sorting. I won't do the math. Yeah, so if we just did the second mode, the code would look like this. Right. And let's see. Still pretty similar. I mean, different ordering.
It's a little different. Yeah, no, it's a little different.
It's a little different. The ones at the, well, I guess US, yeah.
Yeah, it's pretty different. Actually,
Yeah.
surprisingly different. Just like the first and last happen to be the same. So.
Yeah.
Cool.
Yeah. Anyhow, I think we're going to get into more sophisticated. I like this data set now. I may use it for other demonstrations for other algorithms. The good news is that we've done all the preliminaries that we need for the course. And next week on Monday, when we meet in person again, we will actually cover our first learning algorithm, which is logistic regression. And I hope that you guys have learned a little bit about linear algebra. You've learned a little bit about Bayes' rule and a little bit about MATLAB. And I will see you all in person on Monday. Thank you guys.